Thank you to the organizers for the invite to this meeting. I think it's a very exciting time to be coming together to talk about these very remarkable transients that we're currently studying throughout cosmic history, in fact. And I think it's particularly interesting, not only is it an exciting time, but it's kind of particularly interesting the way there are so many connections that we're starting to draw between some of these different classes of emerging transients. And maybe some of those connections in the long run may turn out to be spurious, but nonetheless, it's getting us all thinking about the same kinds of phenomena and the physics that's going on. And so I think it is particularly timely to have this meeting now. So I'm going to be talking about the sort of far end of the cosmic timeline, high redshift GRBs. And so I'm going to try to discuss how long-duration gamma-ray bursts in particular, that's basically what I'm going to be talking about, how they can be used to study the distant universe, and I'll try and make the case that they are very complementary to what you might call traditional methods of galaxy evolutions that are used to study the early universe and reionization, early star formation, the growth of structure, and that sort of thing. Now, sometimes complementary is taken in an uncomplimentary way because it's sort of taken to mean, second best in some sense, or, confirming what other people have already found. I think that's just not the case here. I mean, sometimes it is a matter of confirmation, but I think really this is a genuinely, the windows that we have through the long duration GRBs provide us with access to information which really, in many cases, is almost impossible to get through other routes. And so typically people sort of make best guesses. Well, the good news is maybe you don't have to just make best guesses. Maybe there is access to those questions through long-duration GRBs. So just to open up at the beginning, hopefully this is legible. I see the font is maybe looking a little small. But some key issues in distant galaxy evolution that at least we will touch on in this talk. So one, of course, is the star formation rate density and how that evolves through cosmic time up to high redshifts. It's a very difficult question determining what the star formation rate globally was at early times. Another key question is how much of the ionizing radiation that was being produced by massive stars in the early universe actually leaked out of the galaxies in which it was produced. So typically, ionizing radiation gets absorbed very easily, and it turns out that both of these questions are crucial to the big question, which is, was star formation in the early universe largely responsible for bringing about and sustaining reionization? So it's long been sort of supposed that that's the most likely scenario, that stars are the sort of have the guiltiest look on their faces, and so likely are responsible. But in fact, the above two questions are the key ones, and there are others as well, but they're perhaps the ones that we've really been stumbling over to try and answer this third question, and I think we're still only part of the way there, whatever people might say. And relating to reionization, we'll review briefly what GRBs can bring to the question, irrespective of whether stars are doing the business, what GRBs can tell us about the timeline and the topology of reionization. All of this stuff relates to other issues of global evolution, in particular cosmic chemical evolution, obviously the stars, the generations of stars which may be driving reionization, or also the generations of stars which are enriching the universe in its early phases. And so all of these things had better ultimately work out, and the numbers had better add up. And I'll touch briefly, but not too much, on the other exciting question of population 3 stars and the very beginning of chemical enrichment. Okay, so I want to first of all take our minds back just over 10 years ago now to the first very high redshift burst ever seen, the first redshift greater than 6 GRB. This was one of the really exciting early swift discoveries, and what you can see here from this spectrum, this is of course famously the GRB 050904. Redshift turned out to be 6.3. You can see this optical spectrum here. Here we have the continuum, the power law continuum of the afterglow. Interspersed here are various metal lines within the host galaxy. We then have a damped Lyman alpha absorbing wing here, followed by a Gunn-Peterson trough. So here the IGM is absorbing essentially all the light, and here you have a contribution from the host galaxy as well as the IGM. One thing that was remarkable about this burst is that it was actually detected in short exposures by a 25-centimeter robotic telescope. Now, I should tell you that that actually, in a sense, inhibited some of the follow-up of this particular event because this was reported as being an R-band detection. Actually, it wasn't an R-band detection at all. It was an unfiltered CCD. And in truth, this 25-centimeter little telescope, it was just responding to the light that was sneaking in at the red end of the CCD response before the Gunn-Peterson trough effectively rendered the rest of the light opaque. So a really remarkably bright event. And I have to tell you that in all the subsequent years, we've never seen anything else at high redshift that was quite as extreme as this guy. Nonetheless, this gave us, of course, great hope at the time that we would be able to use GRBs as very powerful probes of the high redshift universe, because there's certainly nothing else we can see with a 25-centimeter telescope at redshift 6. And one might also remark that this is, of course, the only route we have to looking at currently at individual stars at these kind of redshifts. So we're not just talking about galaxies, these are individual stellar events. Okay, so this is bringing the story kind of up to date then, in the sense of this is all of the Swift GRBs up to some point last year as a function of redshift with their peak luminosity of the prompt emission there. And so don't worry too much about the color coding. What you can see, though, is, of course, that the Swift selection function cuts things off down here. Now, the Swift selection function is rather complicated, but the bottom line is, of course, that at high redshifts, we're really only seeing the very brightest events. There's a whole sea of, presumably a whole sea of fainter GRBs at high redshift that we really wish we could get our hands on, but that's not currently the case. And so, well, if we're going to ask then which are the high redshift events, maybe it's these guys here in this box. So you can see that, so that cuts off at redshift 5, and it has taken some time to build up this sample of events here. The very highest redshift ones are labeled with their own names there, but we just have maybe a dozen or a few more, 15 or so, perhaps, that we'd class as very high redshift events. Now, of course, it's very hard work finding these guys. The light is largely, particularly from redshifts greater than 6 or 7, is largely wiped out of the optical, and so one has to move to the infrared, and it is often assumed that we must be, or we could be, missing a lot of bursts up at this end for that reason, and no doubt we are missing some at this end for that reason. On the other hand, we have evidence from smaller but redshift nearly complete subsamples, which certainly argues that the number of bursts greater than, let's say, redshift 5 is only a few percent of all Swift bursts, and so in the end, it is a struggle. Now, the number at high redshift, of course, is the first thing that we may be interested in using as a tool to probe the universe. Because GRBs are associated with the deaths of massive stars, the rate of bursts at high redshift should reflect the global star formation rate at high redshift. And so if we can account for of course we can, we know the cosmological volume element and time dilation, we can account for that, we can attempt to model the luminosity function, and that allows us to, oh, sorry, I missed a point. I forgot animation. There you go. What was the point I was going to make? The point I was going to make is, of course, the most recent results from the microwave background observations now put the peak era of reionization right around about this, redshift 8 to 8.5 sort of range. So that means that these bursts, which a few years ago we would have said were perhaps towards the end of reionization, actually it looks as if we really are probing with the guys in this box, really the key era of reionization. Okay, so the point I was coming on to then is that by counting bursts and modeling them in these samples, we're able to estimate the rate of star formation at high redshifts globally. So we've not so far had to worry about host galaxies or anything of that sort. We just got redshifts and numbers. And of course, the numbers are small, so the error bars are large, but nonetheless, it's been pointed out by quite a number of authors over many years that the rate of star formation you'd infer from those kind of calculations is actually rather high, and perhaps as much as an order of magnitude higher than the star formation rate that one obtains by counting galaxies and trying to figure out how much star formation is occurring in those and going that route. So this is an influential paper from a few years ago by Robertson and Ellis, and so roughly speaking, the green band there is your traditional route, and the black lines there sort of marks out the kind of range that GRBs seem to be telling us. Now, both of these calculations are hard. The GRBs, of course, we have both a small sample and potentially a bias sample in terms of our follow-up capabilities and biases that may introduce. Also, we do know, increasingly there's evidence that the rate of GRBs is affected by other parameters, most probably metallicity or something closely associated with metallicity, and so that means that we should really model that in this whole game somehow, which isn't easy. And in fact, it's not easy for the galaxy people either, because increasingly it looks as if the faint end of the galaxy luminosity function, particularly at high redshifts, is very steep. So one has to know what that faint end is. One has to assume that it carries on as a power law, like everyone always does. And then you also have to stick some kind of lower limit where you decide that the galaxies shut off and no longer form stars. And all of those things are pretty uncertain. And so some assumptions have to be made in turning the galaxies you see into an actual star formation rate. What I would comment is, and I'm not going to dwell on this very much, is that I think the tension here is reducing compared to how it appeared a few years ago, as it was shown in that previous plot. If you take a look at a more recent analysis that Dan Purley put together as part of the Shoal survey, if you look at the raw GRB numbers, let's focus on this top left panel, compared to the red band, which is the star formation rate from, let's say, traditional galaxy studies, indeed, it still seems that the GRBs overshoot the galaxies at high redshift. However, if you follow Dan's analysis and rescale the GRBs essentially by empirically trying to determine the evolving GRB rate to star formation rate ratio, in other words, this should incorporate effects like metallicity, which may be changing over cosmic time the number of GRBs formed per unit star formation, then you discover that now the agreement is really not so bad, at least from this Shoal sample. And this is a sample which is very highly redshift complete, and so that also removes another uncertainty from this calculation. So I think within the errors and plausible revisions which may yet still occur, certainly I think the galaxy people continue to tend to push this band up a little bit as well at these redshifts. Then I think the tension is nowhere near as severe as it once was, and I think it'll be interesting to see how this evolves in the future. So let me move on, dealing with the afterglows now. You saw in the case of 050904 how we had those metal lines appearing. When you see the metal lines in absorption, that allows you to calculate rather detailed abundances if the data are good enough. The data don't come much better than this spectrum that we obtained with X-Shooter a few years ago for 130606A at redshift just about 6. You can see, hopefully, just get a sense of the fact that there are very many lines in this spectrum, so you don't have to count them yourself. But that obviously gives you access to studying a lot of chemical species and working out rather detailed abundances. For this particular case, we found that the overall metallicity is pretty low, around about a 20th solar. Now, bearing in mind that at these kind of redshifts, spectroscopy of galaxies is essentially almost doesn't exist. And even when it does, of course, one is dealing with emission lines, which are very crude ways of assessing metallicity and the state of the galaxies for the most part. And so whilst there are certainly caveats to put on the conclusions one produces from even data of this quality, I think it still gives you a route into high redshift metallicity determinations, which is much better than can be obtained otherwise.
Is that the host or the intervening totals? Is that 0.05?
That's the host, sorry, yeah. Putting that on a plot of a bunch of other GRB host galaxies with absorption line metallicity determinations, well, you can see there's obviously a spread. We now believe that GRBs are relatively hard to produce at kind of roughly solar and above, or maybe half solar and above. So one can say that the absence of galaxies here is maybe not surprising. That's just because they produce GRBs. But at high redshifts, increasingly, the bulk of star formation is happening in subsolar metallicities, and so we have the route, at least here, to tracing out that overall chemical evolution. One might say, actually, it's pretty flat here, and so there isn't very much evidence of evolution, but nonetheless, as I'm emphasizing, I think the fact that we actually have estimates with some degree of precision at these redshifts is quite remarkable. Very briefly, I'll just flash up this plot here, which shows us another parameter which one can extract from GRB afterglows, namely the dust extinction, and you can see that at low redshifts there's quite a range of extinction values that we can measure. One can study, by the way, not just the overall extinction, but the shape of the extinction law, which is something which is also very hard to do otherwise. And at high redshifts, it seems that that goes very low. Of course, there's some kind of selection effect here. If there was a dusty galaxy at high redshift, it might be really tough to find the afterglow, but probably there aren't many dusty galaxies at high redshift, so we think this is probably telling us a story. A point I want to emphasize a bit more is this question of the escape fraction of ionizing radiation. So we saw in the first spectrum how Lyman alpha, neutral hydrogen Lyman alpha, cuts off the spectrum at a certain point, and by modeling the damping wing, which I'll come back to in a moment as well, but by modeling the damping wing, it's possible to estimate, even at high redshifts, the amount of neutral column of neutral hydrogen in the host galaxy. At lower redshifts, it's rather easier. And when we do that, and people have been doing this now for a few years, so this is a kind of update that I'm showing you here of analyses which were previously done by Johan Fimbo and Chen et al. A few years ago. This shows that in most cases, the large majority of cases, when we see a GRB, we see a very significant column of hydrogen in front of it. Now, what does that tell you? What that tells us, very likely, we think, we argue, is if GRBs are representative of the kinds of massive stars which are producing most of the UV light, the ionizing radiation in these distant galaxies, then these random sight lines towards them should be representative of the sight lines, if you like, out of those galaxies into the IGM. So if we want to get UV ionizing radiation out of these distant galaxies in order to reionize the universe, then there'd better be some sight lines to GRBs where we see a very low column density of hydrogen. As it turns out, this really hardly seems to be the case. We have a couple of examples, moderately convincing examples of low column densities towards GRBs. All of the rest of these guys here are essentially opaque to ionizing radiation. So we can ignore those, and we can ask ourselves, what's the escape fraction then if only roughly about 2 in 100 sight lines gives you any kind of column density which would allow ionizing radiation out? And the answer turns out to be, from this kind of analysis, it looks to be about less than twiddles 1%. So a very low escape fraction, much lower, in fact, than people, well, kind of consistent with what measurements people make from galaxy studies around redshift 3, but certainly a good deal less than the assumptions people make for the escape fraction at higher redshifts if you want to reionize the universe. So I think this is very interesting. It's actually, in many respects, underestimating the problem because there's a bias against locating and measuring redshifts for very high column density systems. They'll be typically dusty systems, and so if any are going to be lost from our samples through selection effects, it's going to be those guys. We ignore, similarly, any attenuation due to dust. And the fact is, the neutral gas very proximate to the burst itself is likely to be ionized by the GRB and the early afterglow emission. And so, in a sense, we're underestimating the column. So, is there any hope? Well, yes, possibly. So, if you just look at the right-hand end of that previous diagram, and in fact, then you get a diagram which is one that was produced by Ryan Chornock a couple of years ago, you see that above redshift kind of 5.5 or so, there is a suggestion at least that the average column is reducing, and so if only we had more and we could firm up the statistics, we might indeed discover that the average column density for these very distant bursts is reducing, but nonetheless, these are all still basically opaque. So we still don't get any escape fraction here, but at least there's maybe a trend in the right direction. I'll talk briefly then, I've mentioned the column density within the host galaxy. It turns out that if you have good enough data, and this is our best example, again it's 130606A, then one can decompose this damping wing into a host contribution and an IgM contribution. In this particular case, at least from our analysis of the X-shooter spectrum, you discover that actually all of the attenuation, or the bulk of it, is in the host galaxy, and there seems to be really rather little prospect or little left over for any neutral fraction in the IgM. Of course, this is less than redshift 6, and so people expect that reionization should be largely over by this point, and so it seems to be, but according to these data, we seem to have a more or less fully ionized IgM by this stage. The hope is that in the future, if we can get better spectroscopy, higher signal-to-noise spectroscopy of more distant systems, then we'll be able to establish the local level of ionization to a whole bunch of different bursts in different directions and at different redshifts. Okay, so I think this is more or less the last topic I'm going to cover. So this is the host galaxies. We recently, this is a student of mine, Joe McGuire, recently had a paper accepted reporting the first detections in emission of redshift 6 GRB host galaxies. And so the three that we are calling detections, two of them certainly are detections. One of them you might think is a bit marginal. These are all bursts I've already mentioned for one reason or another. These are all HST images. You can see just about the keen-sighted view, the position of the afterglows indicated by these red circles relative to these galaxies. So that's nice that we've detected them. As you can see, the citizens of Leicester went bananas when Joe's paper was accepted. I'm sure that's what they were celebrating. However, Joe was doing some very serious work and, in fact, decided to try and assess the extent to which these galaxies looked like regular Lyman break galaxies. So that's a bit hard to do with just one band, which is all we had. So all we could do is basically look at the luminosities and the sizes of the things. Hello. Okay, that's something else. I thought that was my get off. Right, so well, what can you say? Yes, they do. So as far as you can tell from the luminosities and sizes, and okay, there are selection effects going on here. We wouldn't have detected them if they were, very low surface brightness and big. But nonetheless, they appear to be perfectly consistent with the kinds of galaxies people pick up at redshift 6 in Lyman break galaxy studies. And so in that sense, we think that this is a route, as we've argued before, to, for the first time, obtain internal detailed internal properties, metallicities, dust estimates, etc., for Lyman break galaxies at these kind of redshifts, which otherwise are really hard to assess. Okay, so I'll wind up. I'll comment that this is a great thing to do with JWST. In fact, we're all ready for the brightest one, having a go with the VLT to see if we can get emission line spectroscopy. But it's a very obvious thing to do with JWST. If you look at all the other high redshift hosts, you discover that they're very hard to detect, which is broadly consistent with this fact that I mentioned earlier on, that the bulk of star formation is happening probably in galaxies at the faint end of the luminosity function. I guess I'm running out of time to elaborate on that, but essentially it allows you, by looking at the number of hosts that you can detect versus the number that you can't detect, to quantify the amount of star formation that's happening at the very faint end, whatever the form of the luminosity function. So you don't have to make any assumptions about that. You can just find those ratios. So last of all then, just a brief look to the future. Perhaps the most tangible future development in the GRB field is the launch, hopefully in 2021, of a new mission called SFOM, this Chinese-French-led mission, which is essentially quite similar to SWIFT. Those of us involved with SWIFT will kind of recognize the basic layout: fast-slewing platform, a burst detector, an X-ray telescope, but now a rather larger and more powerful visual telescope than the UVOT. And the hope is that in the 2020s, the events which are detected by SFOM and any other missions that are flying at that time will have the great benefit of follow-up with considerably more powerful follow-up facilities like the ELT, for instance, showing you here a simulated spectrum to show how just jolly well you can do at that time. So I've kind of run out of time a bit, so I'll just put my conclusions up there. Thank you.
Nial, are we not losing out on some of the low NH GRBs simply because we don't, if we don't see the Lyman alpha trough, we don't determine a redshift?
I think that certainly could be the case at moderate redshifts. I think it's unlikely to be the case at high redshift because you'd see the forest, and that would be, very clear. So.
One of the interesting predictions of the standard cosmological model is that the mass function of collapsed object is exponentially truncated at high masses, and the fraction of the amount of mass that can be involved in star formation drops exponentially with cosmic time as you go to earlier times. So it would be really a fantastic test of this exponential cutoff in the star formation history if we do see an exponential cutoff in the gamma ray burst population as well. And if you ever find the gamma ray burst at redshift 50 or above, that could be basically evidence that the Gaussian, the initial density perturbations were not Gaussian, were not truncated exponentially. So are there any prospects for going to extremely high redshifts?
Okay, well, thanks for the comment. I think it is, I can't necessarily give a very informed answer. I think what at least is clear is that if any source is going to be possible to see at those kind of redshifts, it's going to be a gamma ray burst. And so in that sense, we at least have a source which in principle could be bright enough with suitable instrumentation to see. Of course, the difficulty that we'll face, I imagine, is the rarity of those things. And so I think, to be honest, I wouldn't be optimistic. I think one would have to be looking at a much more powerful future facilities, I think, unless you consider otherwise, to give yourself a realistic chance in terms of the rates. But it would be a superb thing to do, as you suggest. Sure, yeah, it's certainly not trivial because, as you say, all of the light will be moved right through the optical. But with facilities like JWST, at least there, what you could observe in principle in the mid-infrared and at least see the afterglow that way. Yeah.
When you showed the star formation rate versus redshift, I noticed there was a peak well off the curve at z equals 9. I was wondering if you care to comment on the implications of that point.
Okay, so the thing one has to realize is that that's a single event.
Yes, I realize
right.
that.
So I think basically the error bar is pretty big, and I guess the other point that's probably worth remembering is that that was a photometric redshift, and so there's some scope for that being actually rather lower redshift. Still high redshift, but rather lower than the 9 at which it's placed. And so I think it would probably be over-interpreting the data to draw any strong conclusions from that.
So your take-home message on the Lyman alpha escape fraction wasn't entirely obvious to me. If the GRB hosts at redshift above 8 look like the GRB hosts at redshift 6 to 8, is it possible that massive stars could be responsible for reionization?
I think it would get really tough. Okay, you said if they're like at 6 to 8 and we only have 4 estimates in that range, and so, you know, if you allow me to go to kind of, let's say, you know, 4 to 8, let's say, and so I can then build up some statistics, then I think it looks very hard. You'd have to imagine the universe has contrived to send us a bunch of sort of unrepresentative sight lines in the Swift sample to date. And so I think that is going to push you down to very low escape fractions, you know, of order 1% or 2. And typically, when people manage to explain reionization in their modeling, it's by assuming escape fractions of more like 20%. And so you're a long way, an order of magnitude away from doing that. And I think, you know, the sort of games that people often play there, they say, okay, well, maybe the escape fraction is much higher in very small galaxies. But of course, we think at least that GRBs are pretty darn good at selecting very small galaxies. And, you know, so really, it's hard to see that you've got all that much wiggle room, I think. The other point I would make is that the lifetimes that one imagines for GRB progenitors, assuming they're very massive stars, these are actually the populations which should be largely producing the ionizing radiation. And so again, you might say, okay, maybe there are some stars a little less massive, live a bit longer, perhaps they end up in drifting around in their galaxies, and so they can get a little bit of their UV out into the IGM, but actually they're not producing all that much compared to these big guys. So I think it's pretty tough.
One more quick question. Were you invited to any of Jamie Vardy's parties?
Of course, didn't you know?